In this next module, I'm going to talk about the formal types of errors that can occur with hypothesis tests, and directly related to that, the concept of statistical power. Let's review from last week the steps of a hypothesis test. First thing that you do is you define your null hypothesis. That's the straw man that you want to shoot down. Once you've defined your null hypothesis, then you can predict the range of values for your statistic that you expect to see when you do an experiment if the null hypothesis is true. Then you go out and do your experiment. You calculate that statistic. If the statistic is within the range of values that you're expecting based on the null hypothesis, your p-value, the probability of your data, will end up being something high. In other words, your experiment will sort of mesh with the null hypothesis. On the other hand, let's say you do the experiment and you get a value that's outside of what's expected based on the null hypothesis. Then you're going to get a low p-value. The probability of your data or something more extreme is going to be small given the null hypothesis. If the p-value is small enough, you're going to reject the null hypothesis. In other words, your data and your null hypothesis don't match, and therefore you're not going to reject your data, so you're going to reject the null hypothesis. That's the steps you go through in a hypothesis test. And the underlying logic is something like this. Assume A. Assume that the null hypothesis is true. If the null hypothesis is true, then you expect to see a certain thing in your study. Let's say that you don't see that. So if A, then B, not B. If you don't see that, then you're going to reject your original assumption. That's the logic of a hypothesis test. But because we're doing statistics, we're of course dealing always with uncertainty. We have to grapple with uncertainty. So now throw in a bit of uncertainty. If A is true, then probably we're going to see B. If we don't see B, then probably A isn't true. There's uncertainty thrown in. So at the end of the day, we have to make a binary decision. We either reject the null or we don't. That decision can have some errors associated with it. Let's say that the null hypothesis is true. There really isn't an effect. But we erroneously reject the null hypothesis when we shouldn't. That's a false positive. We've made a false positive. We call that a type 1 error, sometimes also called an alpha. On the other hand, let's say that the null hypothesis is false and there actually is an effect, but we failed to reject the null hypothesis. That's a false negative error. We call that a type 2 error. It's also known as beta. Directly related to the type 2 error is something called statistical power. Statistical power is just the complement of the type 2 error. It's the probability that if there really is an effect, if the null hypothesis is false, it's the probability that we're actually going to find that effect in our study. Notice that all of these have a sneaky little conditional. You can only make a type 1 error if the effect isn't real, if the null hypothesis is true. You can only make a type 2 error if the effect is real, if the null hypothesis is false. So just kind of keep that in mind. I think the easiest way to understand type 1 and type 2 error is to put them in a little box. And I'm going to do that in a moment. But whenever I talk about type 1 and type 2 error, it always reminds me of something called Pascal's wager. So this is a little bit of an aside. But I was a philosophy major in college. And if you've ever taken a philosophy 101 class, you probably had to read a bunch of proofs from philosophers throughout history about either the existence or non-existence of God. Philosophers love to think about that and talk about that in the philosophy literature. One of my favorite proofs of all the ones that I've had to read was something called Pascal's wager. And I really like it because it's simple. It's a simple, logical, rational argument rather than these kind of long-winded, drawn-out proofs that were hard to read. Pascal's wager was just a rational argument. So Pascal says there's some truth out there. Either God exists or God doesn't exist. One of those things is true, and we can't really ever know for sure. You have to make a decision, however. So it's kind of immaterial what the truth is, since that's, unknowable, but you have to make a decision regardless. Your decision on earth is you're either going to reject God or you're going to accept God. Now let's say, this is Pascal's argument, let's say that God exists and you reject God. Then you've made a big mistake, right? That means you're, depending on the religion you subscribe to, you're going to hell or some bad, very bad thing will result. So that's a big mistake. On the other hand, if God exists and you accept God, then you've got it right, and there's some kind of big payoff, like you're going to heaven or whatever whatever the particular religion you subscribe to says. It's always a big, really great thing. On the other hand, let's say that God doesn't exist, and you reject God. Well, then you've got it right. But the payoff maybe isn't so big. Maybe you get to live your life a little bit differently, but maybe the payoff is not huge there. However, if God doesn't exist and you accept God, then Pascal says that's really kind of a minor mistake. The cost to you of that mistake isn't so high because, maybe you live your life a little bit differently. Maybe you go to church or temple. Maybe you don't drink as much. But he says that those costs are much more minor compared to the other mistake you could make. And that's his sort of rational argument for whether or not to believe in God. So I think it's just an interesting and fun example. And it always reminds me of type 1 and type 2 error, because put type 1 and type 2 error in a box. So the null hypothesis is either true or it's false. One of those things is true, and we can never really know with complete certainty. Let me just throw an example in here. So let's say that your null hypothesis is that the vaccine, the HIV vaccine, like we saw last week, doesn't work. That's the null hypothesis. So let's say that one possibility is that that's true and the vaccine actually doesn't work. If the null hypothesis is false, that would mean that the vaccine actually does have a biological effect. Now you got into a study, and then you have to make a statistical decision. You're either going to reject the null hypothesis and conclude that, in fact, the vaccine does work, or you're going to fail to reject the null hypothesis. If you fail to reject the null hypothesis, you're not saying that the null hypothesis is true. You're just saying that there's insufficient evidence to reject it. Notice that that's a slightly different thing, so just kind of keep that in mind. We're never proving the null hypothesis. We're just failing to reject it. So let's say that the null hypothesis is true. In fact, the vaccine doesn't work. But let's say that you look at the results of the study and say you see that p-value of 0.04 that made it under 0.05, and you decide to reject the null hypothesis and conclude that the vaccine is effective. Then you've made a type 1 error, a false positive. And we think of that error as being fairly egregious, right? Because you might then go out and give people the vaccine. You might make policy decisions. You might change how you treat patients based on rejecting a null hypothesis. So we tend to guard pretty stringently in the medical literature, or try to, against type 1 error. On the other hand, let's say that the vaccine in fact does work. It has some real biological effect. In other words, that the null hypothesis is false. But let's say you look at the results of this study and the p-values are kind of marginal, you're not that convinced, so you don't reject the null hypothesis. Then you've made a type 2 error, a false negative error. You have failed to find an effect that actually exists. Again though, when you fail to reject the null hypothesis, you're just concluding that there's insufficient evidence that the vaccine works. Therefore, you might decide to keep on studying it. We tend to think of a type 2 error, therefore, as a little bit less egregious because we don't tend to change medical treatment and change policy based on it. The result of a type 2 error is usually there's further study. So in the medical literature, we tend to set the type 1 error rate to be more stringent than the type 2 error rate. And of course, there's going to be a trade-off between those two things. So if you set the type 1 error rate to be more stringent, you have to loosen the type 2 error and vice versa. In the medical literature, a typical study might have a type 1 error rate of 5% and a type 2 error rate of 20%. Again, the type 1 error rate is directly related to the significance level. So this is the false positive rate, the probability of finding an effect that isn't real. If you set the statistical significance cutoff at a p-value of less than 0.05, so in order to be statistically significant and reject the null, you require a p-value of less than 0.05. That means that you're permitting a false positive rate of 5%. If there's nothing going on in your data, if there are no effects, you're still expecting to see a significant p-value 1 in 20 times. That's the type 1 error rate, again, directly related to the significance level. The type 2 error rate is the probability of missing an effect, again, a false negative. Now, we don't usually talk directly about the type 2 error in medical studies. What we do instead is talk about something that's the complement of the type 2 error. We talk about the statistical power. So statistical power is just the probability of finding an effect if it's there. It's the probability of not making a type 2 error. That's usually what we talk about in medical studies. When we design studies, a typical study might be designed to have a power of 80%. So that means we're allowing a false negative rate, a type 2 error rate, of about 20%. That's where your typical study. That means that when we go out to do studies, we're accepting that in about 1 in 5 studies, we're going to miss a real effect. When there are actually effects, we're going to miss about 1 in 5 of them. Statistical power is such an important concept in medicine, I'm going to spend now a few more minutes talking about it. Again, statistical power is the probability of finding an effect if one is there. It's akin, when we talked about diagnostic testing, we talked about something called sensitivity. Statistical power is just akin to sensitivity. If there is an effect, it's the probability that you're actually going to find it. Finding an effect means coming out with a significant p-value at the end of the day. The statistical power is essentially, if there's an effect there, it's the chance that you're going to end up with a significant p-value at the end of the day. Your p-value is going to be under 0.05 or whatever you set the bar at. So statistical power is directly related to p-values because it's the probability of getting a significant p-value. What factors affect p-values? Because the same factors that affect p-values are going to affect statistical power. So let's just review from last week. What affects the p-values? Well, there were three things that affected the p-values. Remember, we were calculating either z or t scores when we do statistical tests, and those were directly related to the effect size divided by the standard error. And the standard error is some composite of variability divided by sample size. It's not exactly variability divided by sample size. It's more complicated than that, but in essence, the standard error has variability in the numerator and some version of sample size in the denominator. So roughly, our z or t score was always proportional to the effect size divided by the variability divided by the sample size. That actually puts the sample size essentially in the numerator. Bigger z-scores and bigger t-scores mean smaller p-values. In other words, if you have a bigger effect size, that's going to decrease the size of your p-value. It's going to make you more likely to find a statistically significant effect. If your sample size is bigger, you're also going to be more likely to find a statistically significant effect. However, if you have greater variability in the outcome or trait you're looking at, the greater the variability, the smaller the z or t value, therefore the less chance you'll have of finding statistical significance. So those are the three factors that factor into the p-value. Well, since the statistical power is just the chance that you're going to find a significant p-value, of course power is directly related to all those factors as well.